And we're back. So today we'll continue our conversation on inference specifically max likelihood estimation. And so administratively, the reading is in the text, chapter 9, in probability and statistics for computer scientists. Project 3 is due this evening on Thursday, 2nd of April, 2020 at the usual 1 second before midnight, which is 11:59 and 59 seconds. In Project 3, it is an implementation of PLA, perceptual learning algorithm, on a synthetic data set for the credit classification problem, and there is a written part that counts for homework 3. Okay, so please make sure you get that in on time. All right, so where we last left off, we talked about optimization, and this optimization problem is to find the setting of parameter lambda that maximizes the log likelihood over all the observations. And this log likelihood involves a sum, and that sum stems from our monotonic transformation, namely natural log, of the product of the marginal likelihoods. And so we have this expression, lambda hat is the result of finding the lambda, argmax lambda, so lambda are our feasible solutions. So we're going to test various settings for lambda to find the lambda that gives you the maximum value for this expression. And so this expression is our objective function. Objective function. Our feasible solutions are all the lambdas. So that lambda is our feasible, my scribble, solution. Solutions, plural, because we have more than one feasible solution, and we're testing each one to see which one achieves a maximum for the objective. And then the lambda that achieves the maximum, we're calling it lambda hat, and it's called lambda hat because it will stand in place as a good, stable replacement for unknown population parameter lambda. Okay, so of course, being from Massachusetts, I would be remiss if I did not have a Kennedy reference in there. And so,
ask not what your country can do for you, ask what you can do for your country.
Okay. So, for the good of your models, ask not what lambda can do for you, rather ask what you can do to get your lambda. So continuing on, I want you, yes you, to find the lambda that maximizes this expression. And so we have the log of the joint likelihood. So here, our P of X, let me switch pens here. Oops. Let's try, nope, not green. Let's try blue. Okay. And so here, our P of X, that's our joint likelihood. Joint likelihood. Likelihood. And that involved the superproduct. We take the natural log of it, and that's where we get the sum. And then we take the log of the individual marginal likelihood, and we got this expression, which was the log marginal likelihood for the Poisson distribution. Okay, and so we want to maximize this expression. We want to find the lambda that maximizes this expression. And there are a number of ways in which we could do this. So let's brainstorm. How might we find the maximum of this objective function? Now recall these x's, these xi's, those are constants. Those are actual values or observations, right? So you might have, an x is equal to 1 event that was observed, another x I might be 10 events that were observed. So these are all constants. The free variable here are the lambdas. So that lambda, those are the free variables. Everything else is the constant. And so in order to maximize this expression, our feasible solutions are all the possible values that lambda can take on. So we could try, okay, lambda equals 1, lambda equals 0.7, lambda equals 1.5, lambda equals 20, all sorts of possible values for your set of feasible solutions. They could be the best ones, but you have to check. And so if we want to maximize this expression, it's really asking the question, how do you find the maximum of a function? Now, this particular function, because all the xi's are constants, they're data points, this is really a function of lambda, right? So depending on what value you have for lambda, well, this lambda is going to be set, that lambda is going to be set, and this expression is going to take on a value. If you input a different value of lambda, that expression is going to take on a different value. So how do you find the maximum of a function? So this particular function is f of lambda, but when we talk about things mathematically, we often call a function f of x instead of f of lambda. So in this demonstration about how you might find the maximum of a function, I'm going to use f of x, but when we decide what method is going to be the best way to find that maximum, we're going to go back and try that result on f of lambda, this particular f of lambda. Okay, so generally, if you have some function f of x, how would you find, or how might you find the maximum of that function? Well, let's take a look at this. You could do sequential search. So let's say you have a possible set of values, x. So let's say let's define x, right? And let's say this box here is all the different values that x can take on. It can be 0.001, it could be 0.127, maybe it could be 1.4, it could be 27.3, it could be 100, it could be 25, whatever. So if you're going to search for the maximum of a function, well, one thing you could do is this sequential search. What does that sequential search mean? In this particular case, it means you take all the values and you put them in some order, like 0.001 would come first, 0.127 would come next, 1.4 would be followed by 25, followed by 27.3, followed by 100. So then once you put them in some ordering, you then try each one. You first try this first one, you try the second value, you try this third value, you try the fourth value, you try the fifth value, you try the sixth value, and so forth. So sequential search means you move through all the values in order that this free variable, this unknown set of feasible solutions can take on. The next one is randomized search. Randomized search, as the name implies, and you'll see this in a moment, you're going to not do it in sequential order, but you're just going to randomly choose some value that the feasible solution that can occur. And then there's another technique that we'll kind of defer for later. So let's take a look at how this might work. So this is sequential search, and along the horizontal axis, we'll put our values of x, our feasible solutions. And so for each tick mark along this horizontal axis, that represents a different value of feasible solution that we can consider, a value that x can take on. Along the vertical axis, that's the value of our objective function given that feasible solution x, so that's f of x. Okay, so sequential search says, well, we start at some starting point, and this is imagining what our objective function looks like for different values of x for our feasible solutions, the red curve. So we try out through some low and some high interval. So low, in this particular case, the previous slide, would be 0.001, and high would be 100. So we have the low and the high end of our interval describing the set or the bounds on the set of feasible solutions. And we start out with some initial value, x1. That's our first feasible solution. So what do? We evaluate the objective function. Okay, that's f of x1. So we remember that point, and now we ask the question, if we continue to try our feasible solutions in sequential order, whichever one is the greatest value, f of x, that the objective function takes on, that's going to be the feasible solution, the optimum, the one that maximizes our objective function. So that's what's going to be ultimately our lambda hat. So let's take a look at this. So we try x1, and we get an output f of x1, okay, for our objective function. Then we go in sequence to the next one, x2. We evaluate our objective, f of x2. Now here you see that f of x2 is greater than f of x1. So now our next best feasible solution, we replace it. It's no longer x1, it's now x2. All right. So we try then some other one, x3, x4, x5. We continue doing that. And then at some point, there's some feasible solution associated with the maximum value of our objective function. Let's call that xm, where m stands for maximum. We evaluate f of x on this xm, so that's f of xm. We remember that value, and because it's the maximum, every subsequent feasible solution that we try through our sequential search, its evaluation on the objective function, if we evaluate the objective function on those sequentially following feasible solutions, they're going to be smaller. So we're never going to replace our current understanding of the best of those feasible solutions. So we try the next one and the next one and to the next one until we get to the high end of this interval, xn, and we're done. Okay, so if we do that, all right, we evaluate the last of the feasible solutions in our sequence. We get f of xn, and we hang on to this xm as being the largest among the feasible solutions. Something happened there. Okay, great. So is there a problem with this? Let me have you press pause and think about what the problems with this could be. So we'll wait for a few seconds. Please press pause. Okay, now that we're done, we ask the question, is there a problem with this? Well, let's see. Well, first, it takes too long, and it's not guaranteed to find a maximum. Let's explain what I mean by that. So if you want to make sure that you're going to precisely catch this xm, that best feasible solution where the objective reaches its maximum value, well, you might want to make sure that each increment in your sequential ordering of feasible solution is very, very small. And if you have a very, very small number of increments between the low end and the high end of your interval for your feasible solutions, you're going to have a lot of them to evaluate, and it's going to take a really long time to do it. The other point about not guaranteed to find a maximum, suppose if your separation between feasible solutions that you try in your sequence is relatively large. So let's say the distance between each feasible solutions is this. So I would try x1, the next two, and if I do this in regular increments, well, I'm not always guaranteed that I'm going to evaluate xm. So here I evaluated this feasible solution, let's call that xi, and I evaluated this feasible solution, xj. So I would either reach this point as a maximum or this point, f of xj, as a maximum. This would be f of xj, and this point here would be f of xi. Now, as you can see, f of xi and f of xj, they're not the maximum. xm is. But I never evaluate or consider xm because the way I've chopped up the increments to define the sequence of feasible solutions sequentially, it is too big to capture anything that's remotely close to this xm. And so for that reason, I'm not guaranteed that I'm going to find the maximum. It takes too long if I try to find the maximum by making these slivers very, very small. But if I want it to take not too long to run in a reasonable amount of time, then I'm not guaranteed to find the maximum. Okay, so there are some problems there. So what if then we'll strike that off from consideration and we'll try something else. Let's try randomizing that search. All right. So again, we have the same scenario. We have the low and the high point for our interval, and all the values in between in this interval along the horizontal axis represent the set of feasible solutions that we can try or evaluate. So randomize, okay, that means I can get any value and I select them randomly. So let's try this out. So I try my first value that I randomly select, and because it's now randomized, the first random selection can be anywhere in this interval because it's uniformly distributed, this randomized selection. So I just happen that this x1, the first feasible solution I consider, the randomizer picks this value. Okay, great. So I evaluate my objective function at my first randomly selected feasible solution, f of x1, and I remember that. Okay, so now I make another randomized selection, let's say x2, and x2 just happened to be picked over here. It's randomized, so any value in my set of data values for feasible solutions, anyone is equally likely to be selected. So let's say x2, my second randomly selected feasible solution, I try that x2 there, I evaluate my function. Now, in this particular case, f of x2 is greater than f of x1, so now my current best feasible solution, I'm going to call that x2. Okay, so I repeat this process again and again and again. x3, I try that, evaluate it. Oh, it's smaller than f of x2. So I discard x3 and I hold on to x2 as being my best among the feasible solutions. Okay, so I keep doing that again and again and again and many times. And on that nth one, I evaluate f of xn. Now, of course, certainly I could do this. And if I do this enough times, I hope to, maybe I might not, get enough coverage for slivers close enough together that I'm going to select the true best feasible solution. Now, let me ask you, is there a problem with this? I will let you pause the video. Please pause the video, think about it, and come up with an answer. So, is there a problem with this? We'll wait a few moments for your pause. Okay, we're back. Is there a problem with this? Yes, there are problems with this. Now, you don't know how long to conduct the search. If n, the number of randomized points, is very large, you're going to get a lot of probes, if you will, in different locations representing different types of feasible solutions, large ones, small ones, something in between. But we don't know how big n should be, how many probes or selections we should make. It might be 10, it might be 100, it might be 1,000. So we don't really know how long to run this search to get a good value that's somewhere close to this best feasible solution here associated with the peak of our f of x. This can possibly take a very long time. If the difference between low and high is very large, and you want to have good coverage of different parts of the space of feasible solutions, you're going to have to sample a large number of times with the hopes that this uniform at random sampling is going to cover everywhere or enough different representative locations in our set of possible feasible solutions. So what that means is just about every region of the line has been sampled. So maybe this region of the line, 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 and so forth. So this can take a very long time, especially as n, the number of randomized samples from your feasible solution, n gets large. You can also have repeated values, and that's sort of a waste of computation. If you're doing randomized selection and you select x3 on the third round, maybe on the 100th round, you select either x3 or something very close to x3. Right? That's a waste of computation because you're effectively evaluating this function for all intents and purposes at the same rough point in your set of feasible solutions. It's better spent in some part sampling this evaluation of your objective function, sampling some region that has not yet been explored or considered or evaluated. So you don't know how long to search. It can take a very long time as the number of samples increases, and you can have possible repeated values. Okay, so let's strike randomized search from consideration. That's not going to work. Is there anything else? Can you think of anything else? Well, let's consider that. We'll pause for a moment. Please pause the video and think about, is there something else you can do? So I'll wait for you to pause and we'll come back. Okay, and we're back. So is there anything else? Well, let's first take a look at the following scenario. We have our set of feasible solutions, and these are all the values of x that we're going to consider. And on the vertical axis, that was the horizontal axis, but on the vertical axis, we have the value of the objective function evaluated at each point in the set of feasible solutions. So let's draw a tangent line. And what we're going to do, of course, because it's a tangent line, it comes into contact with our objective function, f of x, at only one point. And so the slope of this tangent line represents the slope at that particular point that it comes into contact with the objective function. So this particular configuration, that's the slope at this value. Okay? So if we slide that tangent line along the function, we see the slope changes. Here it gets larger, and then it gets smaller. It gets larger a little bit, and then it gets smaller. It gets larger, and then wait a minute, now it gets smaller, it gets more negative. So here it was getting more positive, and it got more negative. And we see at this peak, the slope is exactly 0. So let's examine this a little bit more closely. The slope is 0 at the maximum of the function, or at the places where the function turns. Okay? And so let's take a look at this even more closely. So we had, when we were on the increasing side of that function, the slope was positive. And then we went to the decreasing side of that function, the slope was negative. So if you're going to go from positive to negative, you have to go through 0 if you're going to go from positive slope to negative slope. And so, of course, slope is rise over run, the change in y, or the change in the value of the objective function over run, which is the change in the feasible solution. And so because of that, we know that at the maximum, the slope is 0. So what do? We say, okay, well, let's use that idea, and we then take the expression for our objective function, and we set the slope of this objective function to 0 and solve for this unknown lambda. Okay, and that value of lambda, or in the case of this function f of x, the value of f of x, where the x where f of x achieves its maximum, is going to be that value of x for which the slope, or the derivative of f of x, achieves its 0 value. Okay, so we're going to take the derivative ddx, so the derivative with respect to x of f of x. Here, the objective function is some function f of lambda, right? It's a function of lambda because each one of these x's, that's a constant because it's a data value. And so for us, we're going to take d lambda, the slope with respect to lambda, of our f of lambda, where f of lambda is our objective function. Okay, we're going to set that slope of the function to 0, and then we're going to solve for the unknown, which in this case for f of x is going to be the x. Okay, so for the good of your models, I want you to find the lambda that maximizes this expression. Now, this expression just happens to be the result of applying that monotonic transformation, log, on the joint likelihood. This is the joint likelihood. That gave you the log of the superproduct, or the product of marginal likelihoods, and now we have the sum of the marginal log likelihoods, which for the Poisson probability mass function is this expression. So now we want to find this function. This entire function, that sum of the marginal log likelihood of the Poisson probability mass function, that's going to be our f of lambda. So we want to maximize this expression. Okay, so we do that by taking the derivative with respect to lambda, and if we take the derivative with respect to lambda of the log joint likelihood, well, you take the derivative with respect to lambda, both sides of equality. So now we have d lambda of our objective function. The sum I goes from 1 to n of minus lambda plus xi ln lambda minus ln of x factorial. Okay, so now we're going to set this expression to 0 and solve for lambda. So if we do that to the left-hand side of this expression, the log joint likelihood, we're also going to do that to the right-hand side. So we take the log derivative with respect to lambda, dd lambda, of our log marginal likelihood. This is our objective function. It's a function of lambda. And we're going to take this derivative and set it equal to 0. And then we're going to solve for lambda. Now that lambda is the feasible solution where this objective function reaches its maximum. So that's going to be our lambda hat, okay? Our reasonable, our stable replacement. Okay, so let's do this. If we take the derivative of this expression, we make use of the fact that the derivative of a sum is the same as the sum of a derivative. Okay, so we're going to take we have a sum here, and we're going to bring this derivative inside because it doesn't matter if you sum these all together, then take the derivative, or you take the derivative of the first term and then add that to the derivative of the second term. So the derivative of the sum is the sum of the derivatives. That gives us this expression. So we have that expression equals to 0. And now we're going to transform that through this property to the sum, I goes from 1 to n, of dd lambda of that term that's inside the sum. Now this entire expression, we're going to set that equal to 0. That has not changed because of this idea of the turning point is where the function achieves its maximum. Okay, so now we're going to take the derivative of this expression under the summation. And this is what we get. So if we take the derivative with respect to lambda of minus lambda, well, that's just lambda to the 1 power. That's just going to give us minus 1. If we take the derivative of this expression, remember x is a constant, so that constant remains xi, and the derivative of some quantity lambda, derivative with respect to lambda of ln lambda is just 1 over lambda. Okay. Now this last term, well, it's minus what? Ln of x factorial. If we take the derivative with respect to lambda of that, that looks like a constant. And it is a constant with respect to lambda because it does not involve lambda. So the derivative with respect to lambda, dd lambda, of this third term is going to be 0. So that's just minus 0, which is just 0. So we're left with the sum of, for I goes from 1 to n, of minus 1 plus 1 upon lambda times xi. And this entire expression is set equal to 0. All right. So now we take this expression, and if we do a little bit of algebra, we make the following observation. All right, so if we have the sum, we're summing two terms. If we sum these two terms, that's the same as writing, I'll do it up here, the sum I goes from 1 to n of minus 1 plus the sum I goes from 1 to n of 1 upon lambda xi. Okay? Now, that's due to the associative rule of addition. So here, you're taking this term, and then you're adding it to the next version of this term, and then you're adding it to the next version of this term. Now, instead of adding these two terms first, you could add all the minus 1s together underneath the summation, and then add all of the 1 upon lambda xi's together, and then take those two results and add them. That's the associative rule of addition that we're taking advantage of. So if we do that, we get these two sums. Now, of course, this first term is going to be, let me draw an arrow, not equals to, is going to be negative 1 summed with itself n many times. That's just minus n. Okay? And then we add to that this expression. Well, we have 1 over lambda. That does not involve our index I, so we can bring that out of the summation. So we get 1 over lambda. The sum, I, goes from 1 to big N of xi. All right. So if we do that, we get the following expression. We have minus n. We have 1 upon lambda. The sum, I, goes from 1 to big N of xi equals 0. That equals 0 is still there because the whole point was to take the derivative of this objective function and set it equal to 0. Okay? So now, of course, we do a little bit of algebra. We can take this expression and then we add both sides of equality. We add n plus n to both sides of equality plus n. If we do that, well, what do we get? Well, this minus n and plus n, that goes to 0. So we're left with just this term. And then 0 plus n is just n. So we wind up with 1 upon lambda. We have that sum, xi, I goes from 1 to n, is equal to n. So then if we take that expression, we multiply both sides of equality, we divide both sides of equality by n, right? If we do that, you have 1 over n here, and you have a 1 over n here. Now, if you do that, this n and this n cancels out, and this n stays there. Okay, so what you're left with, and then you multiply both sides of equality by lambda. So you multiply by lambda. Here's a lambda. Here's a lambda. Okay, so what happens? So this one went to 1, and this one was 1 over n. So if you multiply both sides of equality by lambda, well, this cancels out, goes to 1. And this lambda times 1 is just lambda. And you're left with 1 over n. The sum, I, goes from 1 to big N, is equal to lambda. Okay. So now that is our definition of what lambda is. We have lambda is equal to 1 over n. The sum, I, goes from 1 to n, xi. Well, that's nothing more than just x bar. And we have a concrete value, an actual value for our lambda. And this value of lambda is our definition of the lambda where this objective function achieves its maximum. And so because this lambda is going to be a replacement for the unknown parameter lambda that maximizes this objective function, we're going to call that lambda hat to mean that it is an estimator or a stable replacement, reasonable replacement for lambda. And so we wind up with this result, lambda hat is equal to 1 upon n, the sum, I goes from 1 to n, xi, which is the same as x bar, the central, the sample mean. Okay, so that's just our x bar. So what does this mean? When you're estimating a Poisson distribution from observations and you use the max likelihood estimation approach for coming upon the best lambda value you can choose, you don't use sequential search. No, we don't do that. We don't use randomized search. We don't do that. We're going to use this value x bar because it maximizes the likelihood function over all of the observations by solving for when the slope equals 0, when it reaches its maximum. And this is our solution. So this idea of finding the version of the Poisson distribution, we started out x distributed as Poisson with lambda, and we don't know what the correct version, what lambda we should choose. The lambda we choose maximizes the joint likelihood. We have that super product, I goes from 1 to n, p of xi, where that p of xi, this probability, was the Poisson probability mass function. Okay? All right. And so when estimating a Poisson distribution from observations by max likelihood estimation, the best lambda value you can choose is going to be x bar. Okay. All right. So this version of lambda, lambda hat, in the literature is often written as lambda hat MLE, which is called the max likelihood estimate for lambda. And it's for the parameter of an IID, so-called independent and identically distributed Poisson sample from observations. So you could literally then, if we had that overhead camera instrumenting the number of customers entering a store over a period of time, we could literally just measure the number of customers over time, take the sample mean, and then use that as our lambda, and then in something like MATLAB, sample from that Poisson distribution where we substituted x bar for lambda and ask it questions like how much revenue will we make? How many employees can we afford? And so forth, things like that. Pretty interesting. So that's all I had for today. We will end there, and we will pick up next time on Tuesday. Again, as a reminder, the homework is due this evening on Thursday at 11:59 and 59 seconds on the 2nd of April, 2020. I look forward to your solutions, and I will see you all on Tuesday. Stay safe and stay healthy.